Hello, everyone. It's my honor to be here. My name is Chen. I'm working in Baidu for 4 years, and my work focuses on AI ops, including data center network monitoring, time series anomaly detection, and service diagnosis. Today, I'm going to introduce our work on NetRadar, a data center network monitoring system. There are 3 parts in my talk. Firstly, I will talk about the motivation. Why do we need to monitor data center network? Secondly, introduce the design of NetRadar. And finally, I will give a brief summary. Okay, in order to explain our motivation, I'd like to show you our traffic distribution. The left figure shows the distribution in Baidu. The blue is the internal traffic, and the orange is the external traffic. The internal traffic is 6 times greater than the external traffic, and it keeps going up. Other companies have a similar distribution to Baidu. The right figure is the distribution of Facebook. We can see that the internal traffic is massive. Now, let's take a look at Baidu network architecture. We have hundreds of thousands of servers. The servers are distributed in more than 30 data centers. Different data centers communicate with each other via super core switch. And inside a data center, several servers connect to the same TOR switch directly and form a TOR. Then, several TORs form a cluster. They communicate with each other via a cluster router. And then, several clusters form a data center. Different clusters connect with each other via kernel routers. We can see that the network architecture is hierarchical and very complex, including tens of thousands of network devices. Suppose that device availability is 99.99%. Then the probability of all devices working well is 37%. That means the device failure happens most of the time. Though engineers prepare redundancy for device, root convergence takes time. Application will be disturbed during convergence. For example, when kernel router went down, here, application will perceive network failure before convergence completed. The higher the device is, the more time the convergence will take. Besides, application may perceive congestion when all device is healthy. For example, each server usually connects to the TOR switch with 1G bandwidth, but due to oversubscription, the export bandwidth of the TOR switch is only 3G. The applications may perceive network failure when the total traffic is more than 3G. So, redundancy can't avoid network failure, no matter how many redundant devices are prepared. So it's very important to monitor data center network. Now, let's move to the second part, the design of NetRadar. The key points of data center monitoring are measurement and data analysis. The way of measurement determines what kind of the observations we will get. If the method is not appropriate, there will be no chance to get good analysis results. So let's talk about the measurement first. As we all know, SRE is responsible for applications availability. They care about all the network failures that application perceived. It's a common and effective method to detect device failure based on syslog. Unfortunately, device monitoring helps SRE little because device availability is not consistent with application's availability. For example, due to device redundancy, application may work well during device failure. And applications may perceive network congestion when all devices are healthy. Statistically, 36% network failures that application perceived are caused by congestion, which means device monitoring system will miss 36% network failures. Well, end-to-end probing is one server sending probe message to another. It perceives most the same network issues with applications. Therefore, NetRadar takes end-to-end probing method, which is very significant to SRE. Probing between every possible server pair is the most direct and simple way. But there are hundreds of thousands of servers, then billions of possible server pairs in Baidu scenario. Take 100,000 servers as an example. Every server will probe the others and be probed by the others every 30 seconds with 10 KB message size. Then it costs 533 Mbps for each server, while the total bandwidth is 1 G. We can't afford it, so we have to sample. If we can guarantee sufficient samples for every network path, the samples can still characterize the network quality. So, how to sample sufficient samples for each path with the minimum cost? NetRadar takes the network architecture into consideration. The architecture is hierarchical, so we designed a hierarchical probing method. There are 3 levels. We send the probe message between every 2 TOS in the same cluster and every 2 clusters in the same data center and every 2 data centers. Then the agent is deployed in every server to perform the probe task. The hierarchical probe method ensures that all device is covered with the minimum number of probes. Then the next problem is server pair selection between every source and test unit. In order to ensure coverage, every path should be covered with a similar amount of samples. The NetRadar scheduler is responsible for assigning tasks to server to meet the requirements. For example, here is the sample distribution of Datacenter 1 to Datacenter 2. The samples are evenly distributed across the 4 possible paths. The sample proportion is 25% respectively. In addition, the scheduler will prioritize healthy servers and guarantee load balance to reduce the dependency on the state of server itself. According to the probing method above, we can get the observations. The probing results can be organized into a table. Each row represents a sample, a probe, such as SIP1 sent a probe message to DIP1 successfully. The probe task is from TOR level. The source unit is TOR 1 and test unit is TOR 2. Actually, we can measure the network quality for different protocols via different channels. For each protocol and channel combination, we will get a data table. The probing data tells us the reachability between server pairs, but SRE concerns whether a TOR, a cluster, or data center is unreachable, or whether the message can be sent successfully between 2 data centers or 2 clusters. So, data analysis must be carried out to solve SRE's concern based on the measurement data. For a given network architecture, we can enumerate all possible failures. Then we can detect for every possible failure separately. Take cluster 1 detection for example. We can gather all cluster level probing results with source unit or test unit equals cluster 1. Then we count the samples number and the drops number. We just call them N and K for sort. The essence of detection is to answer the question, is the drop rate too large than usual? Or is the key too large for given N? This is errors detection. This just falls into the scope of binomial distribution. Here I list the formula. We can get the normal drop rate P0 by excluding performing for a period of time. Errors detection has been shared in detail by my colleague this morning. You can refer to the talk Anomaly Detection on Golden Signals. Here is the real network case, cluster 1 failure with 25% drop rate. NetRadar observed the drop rate of cluster 1 increase sharply and sent an alert of cluster 1 failure. Here, the drop rate. But at the meantime, due to half the samples in data center 1 are from cluster 1, NetRadar observed the drop rate of Datacenter 1 increased to 12%. So a false positive of Datacenter 1 failure was sent. From this case, we find that detection separately may trigger false positive with certainty. The samples of Datacenter 1 can't provide any further information about cluster 1 failure. So in order to eliminate the false positive, we should gather all the probing results and make an overall analysis. Firstly, we extend the table tags of probing results. The tag name is as follows: source IP, source TOR, source cluster, source data center, and so on. The tax name list is designed according to the network architecture. The tax value depends on the probing source IP and desk IP. The tags can help us to analyze where the jobs are concentrated. The observations can be expressed as multi-dimensional data after we extend the tag. The dimension is tag name, and the dimension value is the tag value. The probing results from source IP1 to DIP1 can be described like this. Then, each failure SRE concern can be represented by dimension combination. For example, source cluster equals cluster 1 and desk cluster equals cluster 2 means failure from cluster 1 to cluster 2. Failure dimension combination should meet the following requirements: high contribution and high uniformity. High contribution means most jobs are concentrated here, and high uniformity means jobs are uniformly distributed in this dimension combination. Multidimensional data analysis is to find the dimension combination that follows up with the requirements. A little abstract. Now I will illustrate the feature with the cluster 1 failure I mentioned. Here, the samples are all from data center level for simple. There are 896 probing samples with 112 jobs. The drop rate of data center 1 is much higher than ever before. But when we drill down, we find the jobs are concentrated on data cluster 1, and there is no drop in cluster 2, which means the uniformity of data center 1 is very low. So it's almost certain that it's not a data center 1 failure. Cluster 1 contains the whole jobs, TOR1 and TOR2 each half. Cluster 1 satisfies the high contribution and high uniformity and will be treated as a failure. TOR1 or TOR2 only covers half of the jobs, so TOR1 or TOR2 isn't a good choice for a failure compared with cluster 1. False positive will be limited by multidimensional data analysis. This is the basic idea of multidimensional data analysis. It needs to enumerate all the possible failure combinations, then try to identify whether the combination is abnormal one by one based on the features. We will be confronted with combination explosion when monitoring a large-scale data center network. So, how to select a failure dimension combination efficiently? It seems that pruning can help to reduce time consumption. We design an efficient algorithm based on decision tree. Now, I will show you the algorithm process based on the observations of cluster 1 failure. Here are the probing results. The number of packets received is 816, and lost is 80. The jobs is a little high, so now let's start to analyze where the jobs are concentrated. Firstly, we need to divide the samples into 2 groups by a dimension. If one group contains the most jobs, while another contains little after splitting, the dimension is a good choice. The bigger difference between the 2 groups is, the better dimension it is. Considering that high-link distance can quantify the similarity between 2 probability distributions, we select dimension based on high-link distance. We calculate the high-link distance between 2 divided nodes for every possible splitting dimension. High-link distance is 0.36 when splitting by source cluster equals cluster 1, and the high-link distance is 0.24 when splitting by source data center equals data center 1, and so on. So we split the node with source cluster equals cluster 1 because the hailing distance is the highest. Then the left node are the samples with the dimension source cluster equals cluster 1. The other samples are in the right node. We can see that the left node contains the most jobs. For the left node, the samples can be only divided by tall tags. The hailing distance is 0 when splitting with tall 1 or tall 2, which means the jobs are evenly distributed across this node. So we stop splitting this node. Repeat the process for the right node. We select dust cluster equals cluster 1 to divide the samples, which can separate the jobs completely. The new left node covers the whole jobs, and the other has no jobs. The new left job, the jobs are evenly distributed across tools, so we stop splitting in the new left job. There is no job in the new right node, so there is no need to split anymore. After the whole protein process, we get the 3 end nodes. 2 of them contains more jobs than usual. Here. And they are failures. Then we combine the failure end nodes and send an alert of cluster 1 failure. This is the whole algorithm. It can help to select the failure dimension efficiently. As the summary, we introduced NetRadar, a data center monitoring system. The data center monitor system consists of 2 steps, measurement and data analysis. End-to-end probing is used to meet SRE's need. And we design a hierarchical and evenly distributed sampling scheduler to ensure sufficiency and efficiency. In the data analysis part, we propose multi-dimensional data analysis to eliminate false positives and give an efficient algorithm based on decision tree. That's all. Thanks for your attention. Thank you.
Okay, so I have a couple of questions because we face very similar problems at Facebook and we have a very similar solution. So first of all, how do you handle false positive in terms of you have a Hadoop cluster that all of a sudden decides to back up data in another data center? How do you handle with the anomaly detection that there will be in your probes more loss because Hadoop is taking all the bandwidth? And and the second question will be about triangulation. If you provide an alert there is a problem in this cluster or it's a data center problem, do you provide any more information to the network engineer or they will have to deep dive themselves? Like because your unit is a cluster or data center, if you tell them, oh look, the data center is broken, they have plenty of network devices to chase.
I want to answer the second question firstly. This monitoring system is designed for SREs because it can perceive almost the same network failures with the applications. To the network engineers, maybe device monitoring is better because they may concerns the device failures and they may to fix the device and they need the information. And with the first question, maybe when the traffic is massive, so we need to monitoring it. And in order to eliminate another issue of our system, so we sampled about 1% of all the samples. So it may it's not a very pressure on the traffic. I don't know whether I answer your questions.
So for the second question, I'm saying that if the service traffic, let's say Hadoop, is overloading, congesting your cluster, then your probes will be, a higher percentage of probes will be lost. So in this case, like Hadoop is having a big transfer. They are fine with having loss because that's the way they do. But if you have other services in the cluster, they will still have loss. How do you use that information then? How you detect it's service induced and not network induced?
For this question, our system can only collect whether the network is congestion. We don't know which product makes the congestion. We can give the observations, and maybe our network engineers have the data about which product has the most traffic, and then we can gather the data and to find the product and to help them to down the traffic.
Okay, thank you.
Hi, it was an interesting concept. So I got a basic question. You were talking about probing to monitor the network path, and you said the probes were between the servers to a server at the other location. So in a network world, usually it's hard to predict which path the packet is going to travel because of equal cost multipathing. Since your class topology, it's probably going to mostly using an equal cost multipathing. So how do you get the attribute like which source star or which in your term, I guess it's kernel router or cluster router. How do you find which path it's taking and plotting those metrics? How are you getting that matrix? Because from a server endpoint, if you try to do a probe, it's very hard to predict which path it's going to take the traffic. How you're doing the tooling? Is that a special kind of probe? You said it's a 10 KB. Is that a normal service kind of probe to monitor whether the destination service is up and running, or what kind of mechanism you do?
In fact, we can't control the path which the problem is selected. We just probe the message. Whatever it takes, we don't care whether what path it will go through. We just get the observations whether a tall or cluster is failure, because SRE concerns this. SRE doesn't know whether his or her application will go through which path, so they don't care this.
Yeah, but you are plotting the metrics, right? How do you get the metrics in your tooling? Like you were able to predict it was taking so-and-so path in your outputs, which you were showing, like which source star, which source cluster it was taking, and you were able to predict the number of packets received through each and every available paths, right? So maybe I don't know if I'm asking too much.
Okay. We have a top. You have top. When the network engineer constructs the network data center, he will know the server, which the server is in which tall and in which cluster and in which data center. The data is all in the department, and we can get the data, and then we can get the tall cluster data center according to the IP, the server IP.
Okay, fine, thanks.
Thank you.
Yeah, I think what you're alluding to is the issue of that you have layer 2 switching, which won't be visible at the IP level if you're doing the probing at the IP level. But typically you will have 2 top of rack switches or 2 cluster switches or routers. And so I think this mechanism is talking about isolating the fault to the role rather than the particular device. Okay. Is that a fair comment?
Yes.
Good.
Yes. Thank you.